please.
Thank you. So first, many thanks to the organizers for inviting me. And second thing, yeah, we have a almost surely we have a postdoc position available next year in so not in Paris but in Nancy. So if anybody is interested, you can contact me. Okay, so I'm going to talk about mainly two things. First of a problem which arises at the interaction between computability and ergodic theory. So I will present the solution to the problem, but I will quite abstract away from this particular problem and present more general results about the difficulty of inverting computably a computable function. So let's go to the problem in ergodic theory. So very basic definitions of ergodic theory. So you take a probability measure on counter space and you say that it is shift invariant if this equality holds. So it just means that the probability of observing a word W at time 0 is the same as at time 1. And as a consequence, it's the same at every time. So such measures have, in a sense, are stable over time. So they do not evolve when time evolves. And because of this property, they have very nice asymptotic statistical behaviors. So the main theorem, maybe the first important theorem in ergodic theory is Birkhoff theorem, which tells you that almost surely the frequency of occurrences of a word along the sequence converge. So it's like it's a kind of generalization of Borel normality. So Borel normality is implicitly for the uniform measure, the uniform coin tossing measure, but the convergence holds actually for every shift invariant measure. The difference with Borel normality is that for the uniform measure, the frequency of occurrences of a word, the limit frequency, does not depend on the particular sequence. It will be always 2 to the minus length of the word. But for shift invariant measures, in general, this limit may depend on the sequence. So for instance, you take two different Bernoulli measures, you take the average, then half of the sequence will statistically behave as the first measure and the other half as the other one. Okay, so if the parameters of the Bernoulli measures are P and Q, half of the sequence will have frequency of one's P and the other half will have Q. So actually, we can put a definition on that and say that a shift invariant measure is ergodic if the limit frequencies do not depend on X. So every Bernoulli measure is ergodic. If you toss a coin, whatever the sequence, you will get the same frequencies at the limit. And yeah. Sorry.
For almost all.
Yeah, almost all. Yeah, right.
X is infinite equal to W?
Is what? Sorry?
X is infinite equal to
infinite. Yeah. Sorry. Yeah. And actually, the Birkhoff theorem holds for every Martin-Löf random sequence. So this is a result of Yugin. Okay, so you can characterize easily being ergodic as not being decomposable. So a measure is not ergodic if it can be split into the average of two different shift invariant measures. So you can see. So yeah, the example about the mixture of two Bernoulli measures is an example of this. Half of the sequences, half of the sequences will behave as P0, as predicted by P0, and the other half as predicted by P1. Okay, there is also a nice interpretation of these notions, that you can see the class of shift invariant measures as a compact convex set in some space, and the ergodic measures are the extremal points. They are the points that you cannot right as a barycenter of other points. Okay. So the point is that ergodic measures have better computable properties than non-ergodic ones. So let me give a few examples. So you take a computable shift invariant measure. So it has been proved that when the measure is ergodic, then the speed with which the frequencies converge is computable, always. And when P is not ergodic, it might be the case that the convergence is not computable. A manifestation of this is that when P is ergodic, Birkhoff ergodic theorem holds exactly at Schnorr random points, while when P is not ergodic, in general, it holds exactly at Martin-Löf random points. But Johanna will tell us more about that on Thursday. Okay, two other examples. So it was recently proved that, which is a kind of generalization of Kuchera's theorem, that if you have a pi01 class of positive measure, or no, it does not matter about the measure, but then the frequency with which a tail of a random sequence falls into C, these densities converges for every Martin-Löf random, and we don't know about the non-ergodic case. So a candidate would be weakly to random, if I'm right, but we don't know whether it's the exact notion of randomness. Another property is that when P is ergodic, the effective dimension of a random sequence always exists. I mean, the effective Hausdorff dimension and the effective packing dimension coincide. And we don't know about the non-ergodic case. Okay, but actually the distinction is not really between ergodic and non-ergodic, but between computably decomposable measures and the others. So let me say a few things about that. So I will not define what it means that the ergodic decomposition is computable, but you can understand this by this characterization. So you take a computable shift invariant measure, and the following things are equivalent. So the speed of convergence of frequencies converge with a computable speed. This is equivalent to, for each random sequence, you can compute from the sequence the limits along the sequence, and you can compute uniformly from X and a bound on the deficiency of X. So this is what we call now layer-wise computable. And this gives, we have these equivalencies. And the point is that not every computable shift invariant measure can be effectively decomposed. So this does not hold for every computable shift invariant measures. And the first counterexample was given by Yugin, who constructed an infinite combination of ergodic measures. And my question was, is it possible to have an example which is only a finite combination? So the precise question is, let P and Q be ergodic measures whose average is computable. Must P and Q be computable? Because the average is effectively decomposable means here just that P and Q are computable. So let us take some height on this problem. So you consider this function which takes two ergodic measures and outputs the average. So this is a very nice computable function, and there is a theorem which tells you that given something, some output, there is only one possible input. So the function is one-to-one. The ergodic decomposition is unique. So yeah, our question is this
permutation?
Yeah. So okay, you can, for instance, take P. You can restrict to P of 0 smaller than Q of 0. I mean, you can order them. So yeah, it's not really 1-to-1, it's 2-to-1 actually, but yeah, we can think of it as 1-to-1. So our question are, yeah, is the inverse of this function computable? And a weaker question, is it computably invariant? Which means, if this is computable, is this computable? Well, so our question is actually exactly this. So, as usual, the answering negatively the first question is much easier because it's not computable for just topological reasons. So let me just show you quickly why this is true. So for every parameter p, you consider this measure, this Markov chain. So it's, okay, at the first round you choose 0 or 1 with probability 1/2, 1/2, and then you choose to change the bit with probability p. So if p is very small, you will get very long blocks of zeros and very long blocks of ones. And when p tends to 0, the measure here tends to this measure, where you have probability 1/2 of having only 0 and 1/2 of having only ones. But the point is that, so this measure converges to this measure in the sense that the measure of cylinders converge to the measure of cylinders, but the ergodic decomposition is not continuous. So this is an ergodic measure, so its decomposition is trivial. It's just, you cannot decompose it, so the only way to express it as an average is of taking it itself twice and taking the average. So this is the decomposition of mu p is just this pair. But this one is not ergodic, because of course all the sequences do not have the same statistics. So the decomposition of this measure is in these two ergodic measures. And so, okay, this converges to this, but the decomposition does not converge. So there is a discontinuity here in the inverse of the average function. So, okay, so it answers easily. I mean, in what I did, there is no computability, it's only topology. So we could say that the inverse of h is not computable just for topological reasons. But our more important question is it non-computable for computability theoretic reasons? So yeah, is there some computable point here whose pre-image is not? So I will show you that the answer is no. We can find a counter example. But actually, I will present you an abstraction of this particular problem. So let us develop a bit about these two ways in which a function is not computable. So you have the class of non-computable functions, and on the left you have the ones that are not computable for topological reasons. They are not computable just because they are not continuous. And on the right you have the functions that are not computable for computability theoretic reasons. So yeah, so computably invariant means that the image of a computable point is computable, not necessarily uniformly. So I mean, it's a nice exercise to try to find points in all this. So I don't know, can someone give me a function which is not computable just for topological reasons? Just a discontinuous function, but if you take a computable point, its image is computable.
You mean just it should be a reverse of some other function?
No, not necessarily. Yes.
What about the one you just gave us?
Yeah, but it's not so simple to see that directly. No, but no, actually it will not. It will be here.
Multiply by 3?
Multiply by 3, yeah. So that's, yeah, right. So multiply by 3 is exactly here. Yeah, so on binary sequences, you cannot multiply by 3 uniformly because
it's real.
yeah. So now a function which is here, so it's non-computable just for computability reasons.
What is there?
So yeah, you have to tell me.
Which function is there? Oh, no function is there? No, what function is there?
What?
No, I didn't understand what you
Yeah.
said.
Which map computable things.
What are there?
Ah, okay.
What
These
is that?
the function for which there is a computable x,
Yeah.
such that
Yeah.
f of x is not computable.
Just the constants for example.
The constant, exactly. Yeah, this is the simplest way. And maybe some function here, which is not computable for both reasons. Yeah, there is a very simple one. The
jump.
Sorry?
Drag jump.
Yeah, the jump. And maybe something here, which is not computable, but for strange reasons. Okay, well, we can cheat and say that every function from the natural numbers to the natural numbers is like that. I mean, it's continuous in a trivial way, and okay, every point is computable. So, but we can encode this into functions from counter space to counter space, for instance. Okay, so we have some examples everywhere. So all these notions are independent, and no one implies the other. Maybe some interesting example is the Julia set. So there is a bunch of results by Braverman and Jampolsky. They prove that the field Julia set is computable in the sense that it is computably invariant. If well, no, it's like this, that you can always compute this from alpha, but not in a uniform way, because the function is not continuous. And there is the Julia set, which is not computable in this sense. There is a computable alpha, such that the associated set is not computable. Okay, so yeah, we see that there are two kinds of reasons for which a function might fail to be computable. And my question is, can we understand when both occur at the same time? So there is a quotation from the tutorial written by Vasco and others that explains exactly what I mean. So functions considered in analysis that are not continuous, that are not computable are often not computable simply because they are discontinuous. So it means often functions belong to this rectangle. A non-computable function may nevertheless be computably invariant. So a function may be here. And if it is not computably invariant, it can be a challenge to construct a computable element that is mapped to a non-computable one. So it can be a challenge to prove that the function is here. Pourel and Richards have shown a general result that shows that for linear operators, the situation is simpler. So what did they prove? That for some class of linear operators, they always fall in this set, which means that either they are computable or they are non-computable in the strongest possible way. And their theorem is roughly that if you have a closed linear operator, then with some assumption, it is bounded, which means continuous, if and only if it is computable, if and only if it is computably invariant. So their theorem has the nice property that it unifies many particular results of computability theory. For instance, there is this construction by Myhill of a computable function whose derivative is continuous but not computable. So you can see this as an application of this to the differentiation operator.
So just boundedness implies computability?
Yes, exactly. Yeah, so there is a hidden assumption here, which just says that the function is not too messy. So it says that there is a dense computable sequence whose image is computable. Yeah, so that looks more.
That's really very.
But this is something that can be checked easily in many situations. So another famous application of this is that there is a non-computable solution to the wave equation. Okay, so yeah, Pourel-Richard's result is so it's limited to linear operators only, and I would like to So first, my question about ergodic decomposition cannot be reduced to their theorems. It does not fall in the assumption of the theorem. So we need another result that gives a similar conclusion, that if a function is sufficiently discontinuous, then it maps some computable point to a non-computable one. So we want to find a strong notion of discontinuity that implies what I just said. So there are several interests in doing this. So the first is to understand better when topology and computability meet. Another is that we could apply this general theorem to many situations, the point is that usually proving that something is discontinuous is easier than proving that it's not computable. So it would give easier applications. So there are already many examples in the literature where this philosophy can be used, that a computability result can be in some sense reduced to a topological one. So there is just what I just mentioned. There is a computable nowhere differentiable function. So an explicit construction has been given more than 1 century ago, but we can think of this as an application of the computable Baire theorem, which was BCT0 this morning, stating that the set of nowhere differentiable continuous function is co-meager, and applying the computable Baire theorem, you can compute a point, a function which is like that. And very similarly, the Kleene-Post theorem can be seen as the same argument, but relativized to 0 prime. Okay, so now let's enter into the main subject. So just one slide of basic definitions from computable analysis. So we will work on effective topological space, which are roughly topological spaces with a countable basis. A point is computable if you can enumerate its neighborhoods. An open set is effective if you can enumerate it as a union of balls. A function is computable if from the neighborhoods of x you can compute the neighborhoods of f of x, and this is equivalent to being effectively continuous, which means that the preimage of basic open sets are effective open sets. And a function is computably invariant if for every computable x, f of x is computable. And we can also say that x is computable from y if there is a machine that, given any enumeration of the neighborhoods of y, enumerates the neighborhoods of x. So depending on the space, we can get Turing reduction here or other types of reduction. So let's take some basic examples. So there is the Cantor space that everybody knows. There is the Cantor space, but where you change the topology. It's like giving as a basis the cylinders with these symbols, which say that the sequence has a 1 here, and you don't tell anything here. So you never say explicitly where there are zeros, but only where there are ones. So equivalently, you can define this like that. So the computable elements in this space are the CE sets. The real interval, as you can imagine, you can also put this particular topology with the open sets are only right semi-lines, and you get the left CE real numbers as computable elements. And another important class is the effective Polish spaces. So Jason defined them yesterday. And this is the spaces with which we will work. So let's go to the first result. So we have a continuous function which is 1-to-1, and so we want to define a notion of discontinuity for the inverse. So okay, there is this usual definition that h is continuously invertible at x if the inverse function is continuous at h of x. Okay, and there is this weakening that says that if you restrict everything to some ball around x, the inverse becomes continuous at that point. So it means, actually it's very easy to understand. You can imagine a game where the player describes h of x, so he enumerates the neighborhoods of h of x, and the opponent tries to find x. And h is continuously invertible at x if the opponent can describe x knowing h of x. And h is locally continuously invertible at x if the opponent wins and given an advice that x is in some basic open set. So okay, so when x is compact and y is Hausdorff, and if h is continuous and 1-to-1, then its inverse is always continuous. So in this case, nothing interesting happens. So we have to remove one of these two assumptions to get interesting examples. So we first consider the case where y is not Hausdorff. So you consider the identity from counter space to counter space, but the topology at the beginning is the usual topology, and at the end it's this subset topology. So the game is like that. The player enumerates a set, and the opponent tries to compute the set. So where does the opponent is able to do that? Well, when A is the whole set of natural numbers. I mean, if I enumerate you the set of natural numbers, then every element will eventually be enumerated. So you will be able to construct the characteristic function of A. If there is a 0, at this place you will never know what will be the bit. What locally continuous invertible means? Well, the same, but you can, if the set is cofinite, then you can give as advice the prefix which contains all the zeros, and the opponent will be able to derive all the remaining part from the enumeration of A. Okay. So we have a very similar phenomenon when we consider this, where the player describes a sequence of rational numbers converging from the left, and the opponent again has to describe A, and we have exactly the same phenomenon. Just a subtlety between counter space and real numbers. It's often the two sets are usually identified as being roughly the same, but there is a kind of there is some difference that if you take the same function but starting from reals instead of binary sequences, then the only place where it is locally invertible is at 1. Okay, another example is unique choice in counter space. So you imagine that the player enumerates the open set, which is the complement of a point, and the opponent tries to describe X. So this is possible. The opponent always wins because the space is compact. So it's just to say that it's a kind of uniform way today to say that if a singleton is pi 0, 1, then the point is computable. Okay, so this is just the uniform topological version of this. And here, the inverse is continuous everywhere. On the set of natural numbers, which is not compact, it's very different. So the player enumerates all the integers that are not n. The opponent will never know what n is. So it's nowhere continuously invertible. But if you give the advice that you are in some singleton, then the opponent wins, of course. In bare space, so this is not exactly the choice as was defined by Vasco, but yeah, you can imagine a function from n to n. The player enumerates the complement of the graph, and the opponent tries to describe f. So actually, the opponent cannot do that. So the function is nowhere continuously invertible. And our example is the ergodic decomposition. So now the player describes the average measure, and the opponent has to find P and Q. And the point is that this function is continuously invertible only at the diagonal. Yeah.
So what is not compact
The
here?
ergodic measures.
Oh, it is the error because it is
Yeah,
the error.
yeah. So let me prove that this thing. Actually, it's very visual. So we want to prove that H is not continuously invertible at this point. So you take two different ergodic measures. You have this average, and you want to change P and Q very much, but keeping the average very close. So the first thing you do is you take two convex combinations of P and Q, which will give exactly the same average. So here you moved much P from P prime and Q to Q prime, but you didn't change the average. But the problem is that P prime and Q prime are not ergodic. They can be decomposed. But the ergodic measures are dense. So you can change them very slightly, and you end up with new ergodic measures that are different from the original one, but their average is very close to the original one. Yeah, so that's the proof. And another example is that, so here we meet Pourel and Richard's result, that if you take a linear map, then if the inverse is bounded, then it is continuous, and if it is not bounded, then it is not continuous in this strong sense. Yeah. And the first result is that, we already have something interesting, that if you have a computable one-to-one map, if a point is sufficiently generic, then either the function is locally continuously invertible at x, or x is not computable from h of x. So it means that if h is not topologically invertible at x, then it is not computably invertible at x.
What is one generic?
So one generic is that it does not belong to the boundary of any effective open set. So let me prove this very simple result. That, okay, you fix a machine, you consider the set C of x C's such that the machine computes x from h of x, and you consider this set U of x's such that so the machine does not compute x, but in a way that it can be discovered one day, that the machine eventually halts and outputs something which is very far from x. So this is a property that you can semi-decide, which means that this is an effective open set. And if h is not continuously invertible at x, then x must be in the boundary of this set. So the proof is very simple. You take this x, you take a ball, and you want to find a point in the ball which is in UM. So you take, because h is not continuously invertible, you can take x prime, which is very different from x, but the image is very close to the image of x. And because the image is very close, the machine on h of x prime must compute something close to x by continuity. So x prime is in UM. Okay, you can discover one day that M does not compute x prime from this. So yeah, this is okay. So now if x is one generic, then it cannot be like that. So it is not in Cm, and then the function is not computably invertible at that point. So we can directly apply this to several examples. So there is this toy example that which is well known, but just to see that it gives something. So if you take a one generic set, then it cannot be computed from enumerating this set. Here we have a partial answer to our question. If you take a one generic pair of ergodic measures, then it will not be computable from its average. And we have something similar for linear operators. But yeah, we didn't. So we know that these functions are in this class. That there exists there exists x, which is not computable from h of x. So we know that these functions belong to this, but we didn't answer. Yeah, we want to prove that they are here. So actually, we have to define another notion which I present now. So first remark, the inverse of h is continuous if and only if h is open, which means it maps an open set to an open set. So a first weakening of this notion is h is quasi-open if the image of every open set, so maybe it's not open, but it has non-empty interior. So it contains a non-empty open set. So this is just a weakening. And another, a further weakening is h is somewhere quasi-open if when you restrict h to some ball, it becomes quasi-open. So maybe it looks a bit mystical, but yeah. So I just show how you can define it formally, but it's not very important. We will see in examples what it gives. So now we define the converse of this. H is nowhere quasi-open if it is not somewhere quasi-open. So it's a strong notion of discontinuity for the inverse of H. So when you write down what it means to be nowhere quasi-open, it starts by for every ball B there is an open set UB in B such that something holds. So first remark, if this is true, if you take some x in UB, then h will not be continuously invertible at this x. So it means that if h satisfies this, it will not be continuously invertible on a large set. So now the game interpretation of this is that if h is like that, then the player can defeat the opponent. So it starts as if x was in UB, and it waits for what the opponent says. And if eventually the opponent discovers that x is in this set, then you can move from x to some x prime outside this set. So you can defeat the opponent. So and this is actually what happens in many basic constructions in computability theory. So let's say some examples. Let's take some examples. So again, this function that takes a set and enumerates it. Well, the player has a strategy for this. To B, you associate the cylinder extended with 0. So the idea is that the player can start to choose some A in this cylinder, and at any time it can change his mind and put a 1 in place of 0. So it will. So if he discovers that the opponent computes a 0 here, then he can put a 1 and he will defeat the opponent. And this will be consistent with the enumeration of A that has been made so far. For this, which maps a real to, which maps computable, in which the player lower semi-compute x and the opponent must find x, you can do the kind of same thing. You start from, in an interval, you start from the left part, and if and you can change to the right part at any time, being consistent with an enumeration from below of the set of the real. So for the ergodic decomposition, what I showed you earlier just gives this, that from if you start from P and Q, you can move them far, being coherent with the current approximation of the average. For a linear operator, also we have easily that the map is nowhere quasi-open. Just using the fact that the inverse is unbounded. We can do the same for this function, but okay, I may skip it. Okay, so now this is the right notion, which will make things work. So we say that H is effectively nowhere quasi-open if, when you express for each B there is U such that blah blah, U can be computed from B. So the first thing is that, which is a corollary of the first result, is that if H is like that, then for generic points, yes, so for each generic point, H is not continuously invertible at X, which implies that X is not computable from its image. So it means that for this class of functions, we go into this this class. I will skip it also. And yeah, the theorem that we were looking for is this one, that if the function is like that, if its inverse is strongly discontinuous in this sense, then you can find some non-computable x whose image is computable. So actually we fall into this. So we can say that for such functions we have yeah, so the inverse is not computable for topological reasons and also for computability theoretic reasons. And the proof of this is a finite injury argument. And maybe you can, yeah, and this is actually what, this proof is what happens in many basic finite injury arguments. So, yeah, so you have these requirements. So RE, the RE is, okay, you don't want that the machine number E computes X. So what does this requirement do? So it is it has a restraint coming from the higher priority arguments requirements that he has to choose X inside a given ball B. So what he does is, okay, if X in B, then I put it actually in UB, which is a subset of B. And if at some stage I realize that the machine ME computes something in UB, which can be discovered in finite time, then I change my mind, and instead of having X here, I move it outside UB, and I keep it in B to yeah, because I do not have the right to put it outside B. So this is the rough idea of the construction. So it, again, on these easy examples, it gives directly this fundamental result. And I mean, if you look at the proof, how it goes in the case of this function, you get exactly the halting problem. Another example is that there exists a non-computable function whose graph is cosine. In particular, it is a pi01 singleton. And if you follow the proof in this case, you exactly get this well-known example. So, I mean, the construction is abstract, but if you look at instances, it gives concrete constructions. So another thing is that, yeah, we go back to this particular result, that there is a computable function whose derivative is continuous but not computable. And we get the answer to our question, which is that there exist non-computable ergodic measures whose average is computable. Okay, so we have this theorem, and we can go a bit further. We can prove this theorem that actually the inverse of H is well, the jump operator is reducible to H minus 1, which means that we can encode the jump into H minus 1. So yeah, the question is, okay, so the first theorem tells you that if you are one generic, you are not computable with respect to this. Now, if H of X is computable, then usually X cannot be one generic. So the question is there a way to reconcile these two theorems and to find some X which in some sense is generic and whose image is computable? So yes, there is. And we will restrict to the case when X is compact and Y is is not Hausdorff. Yeah, that's it. And again, we still have this condition on H. Okay, so we define, given X, we define the upper set of X as this intersection. So a point is in the intersection if it can never be rejected when the player describes H of X. I mean, from the only information given by H of X, you can never know if some element of this set is not X. So this set is a pi01 class relative to h of x. So yeah, we consider the case when y is not Hausdorff because otherwise it's just a singleton. And we get this equivalence that h is continuously invertible if and only if this set is just x, which means that from h of x you can recover x. And locally continuously invertible means that x is isolated in this set. So because of that, we have directly a dichotomy that if h is continuously invertible at x, then it is computable, then x is computable from its image. And for one generic points, we have exactly the opposite. If h is not continuously invertible, then it is not computably invertible. And we define a point to be h generic if it is one generic inside the upper set. So this upper set is a closed set. So it's also a Polish space. So you can define what it means to be one generic in this set. So inside this, there always exists one generic set. Points, I mean. So one generic inside just means the usual notion of genericity, but here you intersect with this set. So if you restrict your view to the upper set, X looks like a one generic. So of course, if you are one generic, you are H generic. If X is isolated here, then it's obviously H generic, but for stupid reasons that this is well, B intersected with this is just X. So either X is in U or X is not in U. Yeah, so we had this result that if H is not continuously invertible at X, which is one generic, then it is not computably invertible at X. But actually, we only need X to be H generic instead of one generic. And we have this theorem that there exists X such that H is not continuously invertible at X. X is H generic and H of X is computable. In particular, X cannot be computable because of the previous slide. But because of this, it cannot be computed from its image. And actually, this construction can be combined with the finite extension method, and the construction also makes X low. So, yeah, actually, I will illustrate on 3 examples. So you consider this, again, this function. So here, a set is subset generic if it belongs to every effective open set that is dense above A, in the sense that you can take elements of the open set containing A arbitrarily close to A. And okay, yeah. Oh, there is. Yeah. I'm almost done. Thank you. Yeah, and so the construction of the theorem, well, the fact that it is H generic, in a sense, it embodies all sufficiently simple finite injury arguments. That such a set has some simple properties. But actually, this notion already exists. It was defined 30 years ago by INRIA, and it was called P generic. So in this example, we get this notion is exactly P genericity. We take this other example. So now the upper set of a real is the right semi-line. So the set of reals that are above A, and being generic in this sense means that you belong to all the effective open sets that are dense above A. And actually, the construction of the theorem is exactly the construction of a Lefsi weakly one generic set. Yeah, another example is that you can consider this map, which takes a closed subset of bare space, of Cantor space, but as input it describes the cylinders that hit the set and the cylinders that miss the set, and as output it only gives the negative information. So this function has all the properties that we have defined, and by the theorem there exists such a pi01 class which is in a sense generic, and for instance this directly implies that such a class has no computable members. So in a sense this theorem embodies many basic constructions in computability theory. Yeah, so now let's come back to the initial question about ergodic measures. So there was this question that if you take two ergodic measures P and Q, if a point is random with respect to the average, is it random with respect to one of the measures? And actually the answer now is no, because you can construct P and Q that compute the halting set, but such that the average is computable. So now if you take a delta 2 random for this average measure, then it will not be random with respect to any of the two measures. And it even provides a measure for an ergodic measure for which Hippocratic randomness is strictly weaker than usual Martin-Löf randomness. Yeah, so now there are several questions that arise from this. So this non-inclusion of random set, is it a rare event, or is it very particular to the example constructed here, or is it true for sufficiently generic pairs? Can we extend the notion of H genericity when X is not compact and Y is not Hausdorff? So and Y is Hausdorff, because in this case the upper set is just a singleton, so it does not make sense to define this. Another question is what happens when, well, instead of considering a function, we consider a relation. So we would like to find a computable Y which is related to no computable X. And another question is related to genericity, is it possible to develop some kind of resource-bounded bare category on the set of points whose image is computable? So yeah, so the idea is that we feel that almost all the points whose image is computable are not computable. So is it possible to give precise meaning to this? And I'm done. Thank you for your attention.
Any question? Yeah. So if we recall the Eugen construction, there was he tried to construct an ergodic example when this not computable. But does he use something specific? Because in your proof it's quite general somehow. You don't use really some ergodic.
Yeah.
So it was also of the same type, or?
Yeah. Actually, his proof is just. I think it's something that happens for sufficiently discontinuous functions. I mean, the idea is that there is a discontinuity, so he defines a computable sequence whose image is not computable using this discontinuity.
So you've got a computable measure, and such that its ergodic decomposition has two measures that both are powerful enough to compute the halting problem.
Yeah.
Is that as bad as it gets, or can it get worse? Is it always possible to
modify
the ergodic composition?
The two measures are always computable in the jump of the.
Okay. And what if it's not just a finite sum of ergodic measures?
Yeah. So there is. Okay, so Eugen example was an countably infinite combination of ergodic measures. So, oh yeah, about so the decomposition, even for infinitely many measures, is always computable in the jump of the measure. Yeah.
Your last statement. That's true uniformly. So you basically
which
have
one?
the complete results that
This one?
ergodic decomposition is equivalent to the jump.
So it's yeah. In that case, yes. But for general H, it's not. So we can prove that the jump is reducible to the inverse, but the converse might not be true in general.
But it is true for the ergodic decomposition.
Yeah. Right.
Thank you.